Okay, good morning again. We are in this second session about pre and post processing, okay, and simulation enabling technologies. And our first speaker. Okay, so our first speaker is Constantin Habes, and he is going to talk about computing Lagrangian coherent structures at runtime. All yours. So is it okay for you if I stand in front of the screen? You see everything? So thank you, Joel, for the introduction. Let me introduce myself a little bit further. My name is Constantin, as Joel already said. I'm working at the New Darmstadt in the group of Holger Marshall. And today I would like to present to you a tool well, especially a function object that lets you compute Lagrangian coherent structures at runtime with like any flow solver you can actually use in OpenFOAM. And already on this slide, you see a flow around the cylinder, and you see like forward time and backward time FTLE fields. FTLE stands for finite time the upper of exponent fields. I will walk you through what these are, what they have to do with Lagrangian coherent structures, how to compute them, and what you can do with them in order to analyze and visualize your flow fields. So what are Lagrangian coherent structures? They represent like the hidden skeleton of unsteady or turbulent flows. What is meant by that? So they are the most attracting or most repelling material lines that occur in a transient flow. So actually, this theory stems from dynamical system theory, but I won't get into detail with that because here our dynamical system is just like the velocity field. So we can order our velocity field in dynamically distinct regions. As you see here on the right side, there is a figure. So you have like material lines, if you consider it a 2D flow, or material surfaces, if you consider a 3D flow, that are most repelling or most attractive. And the most important thing about that is there is little to no transport across these surfaces. So they help you to visualize and analyze coherent moving structures in your flow that don't mix with other structures in your flow. So for instance, if you have like on the top left, the image, there is a repelling structure and the attracting structure. So if you have a fluid that surrounds the intersection with which is a saddle point, the fluid will stretch along the attracting LCS and will be squished along the repelling, or also the fluid will be repelled from this repelling line or surface. And for like eddies, as you see on the bottom, for eddies, these structures or these lines are mostly coincident, and they form like a very complex tangle on such a intersection. But as you can see, they outline this coherent eddy, this coherent moving eddy. So what insights do the LCS give me? I have like two examples here before I go into the detail on how to compute them. As you might remember, in 2010, there was like a real bad environmental disaster from the oil spill of the Deepwater Horizon. At that time, besides like how to stop the oil spill, the most concern was where does the pollution go? So they had the velocity field data from the Navy, and they computed Lagrangian coherent structures based on those velocity fields. And based on those fields, here you see like the attracting LCS. You can see that there is a big eddy, like in the center of the Gulf of Mexico, and there's kind of a border in between. As you can see here, maybe you see my mouse. This is Florida, this is Cuba, and there's kind of like this border where no oil will pass. And so you can then extract from that data that there will no oil pollution be like on the coast of Cuba, but more on the coast of Florida. And another example is the bubble wake, which was investigated by Alexandra von Kameke and her colleagues at HB Hamburg. She looked at the rising bubble, the Taylor bubble, and wanted to know if there are coherent structures arising in the wake of this bubble. Because if you have like a bubble column where you have a chemical species transferring from the bubble into the liquid, and you want this species to react there, you don't want to have coherent moving structures because they hinder your mixing, or large moving structures, because they hinder your mixing and therefore they hinder your reactions. So as you can see, there is a large coherent structure evolving at some Reynolds numbers behind this rising bubble. And you can see like that if there are fluid parcels inside the structure, they won't cross the boundary of this real structure, this LCS. So when I first started to work on these LCS, my question was, why shouldn't I just use like streamlines or streak lines? Because this is like the first thing an MCP engineer would do in computing or visualizing its velocity. So at first, I want to give a short recap on what are streamlines and streamlines. Streamlines are always tangent to the instantaneous velocity. And streamlines are lines that are produced by parcels that have passed through a specific point at different times. Actually, for stationary flows, these both lines are the same. For transient flow, they are not. But you can also not say, when you analyze them, where are structures where no mixing occurs across. So they don't separate coherent moving structures, where you can say there's no like transfer across. So how to compute such LES? There are multiple methods. They are mostly the same, but different in some kind. And the one we implemented or used was the finite time Lyapunov exponent computation. This computation of this finite time Lyapunov exponent is using these steps. So the first one is like you have to initialize a grid of particles, like Lagrangian particles, that you then have to track through your moving or your evolving velocity. This can just be done by like how you normally would track Lagrangian particles by integrating them over time with the standard integration. Then from that, you can compute deformation gradient by analyzing how these particles are separating over time or are converging over time. So you can compute them like with this equation you see here, which is an approximation on the deformation gradient tensor. Then from this deformation gradient tensor, we can compute the right Cauchy green tensor. This tensor, especially, is an objective tensor, so it doesn't matter if the observer is moving. So it will always give you the same values. And especially interesting, this tensor gives you information on how your continuum or your fluid is deforming over time. So the eigenvalues, eigenvectors give you directions and values on how it deforms. So the higher values of the eigenvalues of the right Cauchy tensor correspond to more separation of particles or more like divergence of the flow. Not really the divergence you normally see, but the separation of the particles. So if you compute them in forward time, you get like material lines, or you compute those maximum eigenvalues and then like scale them with this logarithmic expression and then use the reciprocal of your integration time. You get those lines as ridges in these fields where the values are the highest, which give you like lines or surfaces in the field that visualize the most repelling material surfaces. If you do the same in backwards time, so if particles separate the most in backwards time, they will converge or get squished the most in forward time. So yeah, there you will get like attracting material lines. luckily for us, there was already external library available that's called libc2lcs, which was first released by him and his colleagues from the National High Performance Computing Center in the UK. They released it, I think, in 2017. And it's a general purpose library for computing such structures during CFD simulations. It's a Fortran library with C++ API, and it's also fully parallelized with MPI. So it was quite easy after a few changes to make it work with OpenFOAM. However, this library is limited due to the data structure it can use. It can only work with static linear grids. So we did write like a function object, which works as an interface between OpenFOAM and this libc2lcs, which passes the velocity field that is computed by any kind of flow solver in OpenFOAM to the libc2lcs, and also the grid bin. We surpassed that limitation due to the rectilinear form of the mesh that libc2lcs has to use by making available, or by optionally, we can use a different mesh for the LCS evaluation. So you have your normal mesh for your CFD computation, and then you have a rectilinear mesh on top, which is then only used for your LCS evaluation. If your CFD mesh or your simulation mesh is already rectilinear, you don't have to make them at all. Also, you can use regions of overset meshes that are rectilinear. You can choose them to be your LCS mesh, but I will come to that at a later point. So you can specify this function object like any other in your control link, and you have to specify the velocity name. And here, the interesting thing is the integration time, because the integration time says how long will you integrate those or track those particles through your flow field, because that determines like the time span your LCS will be evaluated through. So we validated our function object, and there are a few like common evaluation or validation test cases that are used commonly for LCS computing programs or software. And the first one is the steady Arnold with Raman-Chaffetz flow, or short Habes flow. It's an exact periodic solution of the Euler equation, and we just wrote like a very simple OpenFOAM solver which just sets the velocity fields to these specified values. And then we used the function object to compute the FQE fields for that. And as you can see, because the one thing more, we used no separate LCS mesh because that mesh was really just a cube and was therefore rectilinear itself. So the results show that there is very good agreement for the literature data. Another validation we did was the time-dependent double gyre, which is also like a common validation test case. And here the flow field is just given with the screen function, and then again we just wrote a simple OpenFOAM solver which sets the velocity field such given values, and we again use no separate LCS mesh. As you can see here, these double gyres are rotating the same direction, and they are oscillating along the x-axis. And as you can see here, we also have like very good agreement with the data, and you see those coherent structures around the eddies of the gyres form. Then, as a next validation test case, we also validated against this flow around the cylinder. Here, because of the cylinder in the center of the mesh, it is a rectilinear mesh, and therefore we use a separate LCS mesh, which at that point, for the first trial, we used the LCS mesh, which covered the whole domain. And as you can see here, for integrating or computing the LCS for forward time and backward time, you see those coherent structures forming. So forward time gives you these lines where the flow separates the mode, and backward time is where the process will converge the modes to. And again, we have very good agreement with today. However, computing LCS, because you have to track a large set of Lagrangian particles, is quite costly. So we use that option to use a separate LCS mesh by just using a smaller one, which just covers the region of interest. By that, we can just use like a very much smaller set of particles, which can then also be used for the LCS computation. And again, we get the exact same results, but in a much shorter time because the computations are not as close to us. And then for the first case, the third case, we use this overstep mesh method, and then specify just like the intermediate mesh refinement region, and use that as the LCS mesh. And again, we got the same results, but now that the overstep mesh computations are in itself a little bit more expensive than just using a regular mesh. It was again faster than using the whole the big LCS mesh, but it's still cheaper than using the whole LCS mesh. So that's already from my side. We released that code for this function object. So now it's up to you to like use it in order to compute Lagrangian Coherent structures for your flow and analyze it with that. And we also did like paper for that. It's already in submission for the OpenFOAM journal, and we already released that. Check that out. Now I'm happy to answer any questions. So I'm not sure. Yeah, here, like, so this is the simulation mesh, and then you just like use another mesh, which is not connected to this mesh. It just like relies on the same overall thing. Yeah, this should just show that where it is located based on the whole simulation mesh. Exactly. Yeah, unfortunately not yet. Exactly. Yeah. Yes, I do think so. Because as we are computing the contribution which is an objective, this should be exactly. Yeah. Yes, there is some interpolation. You could use the same grid point, but you don't have to. You just map between those meshes by interpolating. Actually, LCS are not very sensitive on those like little errors in the velocity field. Sure. Sure, you still have to like resolve it good enough, But if your LCS mesh should have like the same grid size and reasons your simulation roundabout, but it's not really necessary to have like the same cell sizes everywhere. So, sure. So your Lagrangian, this is an animation of the evolvement of Lagrangian Boolean structures, but every instance of that representation represents your flow over your whole integration interval. So you can say that there is nearly no mixing for that integration time to evaluate. So the longer your integration time gets, the less transport will occur over nodes. Then you are more certain. But again, if your integration time is longer, you might lose some detailed information. It's also used like in turbulence for turbulence analysis. Yeah. Yeah, exactly. Yeah. Yeah. Yeah, good. Yeah, sure.
Nova, thank you for here. Today, I want to talk about how we can navigate and speed accuracy trade-off for multi-physics simulations. So, just a brief definition was multi-physics simulation. It's the simultaneous simulation of different aspects of the physical system or system and the interactions among them, or the simultaneous simulation of a single process on either multiple time or distance scale. So as we know, we have to put like multi-physics simulation, we have to go to identify the aspects of the system to be simulated. Once we simulate and create a discrete reference model of the system, we will resolve the model and analyze it. So doing this process gives us these techniques of challenges, like how we can integrate the multiple aspects of the process with the memory of the how for simulations of the aspects, solution complexity, accuracy, and efficiency of uniformity, content content, alternative, and of course, performance. That they all come from that what's the exact solution or what's the exact convergence bar. So we have to actually find and try to find what's the errors and how we can run the simulation, find the best solutions for convergence. So it's made it also approximation for us, and it's hard to go through all the challenges. So we are proposing solution for the actually face with these problems. It's called precise computing. Precise computing adds a concept that could control approximation in space and time and make a specific explore application with something of precision requirements. So it means that instead of every or all the parameters with the highest precision as possible, we'll have to and actually try to find out what's the best for the application that we want. So instead of this, because we can precise computing and get accuracy for the application that we want to run. So to do this, first understand what is the impact of the function that you want to study simulation, and then the result on the accuracy and the efficient time to this simulation. And after we then we need to provide an interview or in order to evaluate the trade-off between the speed and the accuracy. To implement history, we have existing problem, transfer problem that and it's force number simulation over its conductor and we consider internal and external conductivities that we make the configured model. And for the solid part, and the fluid part, and we solve the other equations for the fluid part and the energy equations for the transfer. So we want to study different parameters, different electric parameters in this study, in this problem. That is this problem would be stimulation configuration, boundary conditions, physical properties, and material properties. To do this, for running multi-physical stimulation, we need cognitive. And I use precise as a converts the copy of the converts required for the passive of the and the multi-physical environment between existing continuity black or solvent. It's a high-level library function that's giving us mapping data between non-matching grids at the complete interface, point-to-point communication between solver processes, point-to-point escalation. And as you can see here, it's so we need for every point part. That's it's time for the specific problem. So as I mentioned, I needed to study different parameters for exactly how exactly so here, just a good example of changing canister. So when I change the range of canister of the different values of canister, it's like the time, temperature, error average, and the plot for average. And as you can see here, when I do the short canister, so of course, longer decision time, and then, but it's something that I want to just say. You can actually see like really effect on the results like this. So it's true that if you have like a range of different times, still you could have an acceptable accuracy and the result. So you don't have to put all the like the time is getting shorter or like something that you want. And so here we think that decision time versus temperature or average when I change the time step. Here I change the convergence limitation, and here is the text. And so when we change this, we got a shorter decision time, and we still have enough accuracy for running the simulation. So again, it's giving us a sense that okay, we don't have to like we still have a possibility of flexibility to change the parameters, and then it will sense of how we can actually explore the accuracy and the speed of the simulation. So then say that okay, this method could work for this particular problem, and we tried other case studies with the different quantum physics problems for manufacturing. I used another existing open source problem from the first side, and then it was a 2D problem. And again, I started with this. I applied this method in different cases that we made some and we started to plot the from stack and for simulation of this, we use calculates for the solid parts and OpenFOAM for the fluid part. So now we know that okay, how is going to change, and then for the sense of study to what's the problem and how the impacting parameters on the problem. So now, what happens if we have a model, machine learning model, to we could like give it the particular configuration that one, and then it could give us the glitching time and the physical proof error. So now we don't have to check all the possibilities and all the configuration that we say that would work for the simulation. So for doing this, I propose that this model that could give with the simulation configuration, physical properties, material properties, and block conditions, and it would give me predict execution time and physical proof error. And it would be any other parameter that you want. For my project so far, I used this parameter, but it could be any other parameter that would be effective for the multiple stuff. And for applying this, for running this model, I provided three different data sets that covered different parameters of the simulation. So for first data set, I just did a simulation. It was like a different range of the simulation parameters. For the second data set, it was properties, material properties as well. And for the third data set, I trained different boundary conditions as well. And I tried various algorithms for all data sets, like EMM, clear data, and the all the data algorithms and the random forest. And this see was for the random forest regression and evaluated the square or square that you can see. So if we do the random forest, this model with the random forest, I would tell you that random forest regression, we could have like 5% error to predict that how much we could get error accuracy and how long we take the without running this simulation all the time or treating all the population of the simulations. This is my project so far. Which one? This one. It's sorry, it's what it was. What do you think is problem? It depends. It depends on the problem and what solve. For example, there I all of other visitors that working in this area, they need to do the staff graduate sampling performance. But it depends. You can use different, like you can use building algorithm for just applying the what training that you want. If you have restriction for the parameter that you want to study, you just use the building algorithm for applying the steps that whatever the parameter you want to study, and then give these parameters long simulation. It would be any post processing of reasons for sampling the parameters. For this one. For the content was below yeah, we need because it's a multi-physics, so we need this to solve it at the same time with the for transferring data between the customer to transfer what most actually I use precise for all of them, but you use the calculus for the radial path because it's more because what's 3D and more complex structure. I actually Right. Not sure if you started with it completely, but if I know understand truly, it's like asking about how I provide a data set for putting that model, right? Yeah, right. Yeah, so we have to run for this project, for this particular problem that I solved, I had to run the simulation and then provide, but it's not like a big data set, it's not a big data set. And that's a really good point for this to work for all problems because we don't need a huge data sets or huge different scenarios. So it depends on the particular parameter that you want to study. You can run simulation in a different range for each parameter and then provide the data set and then just split this. Yeah, actually the machine learning model would work with this process. It's not like it's yeah.
No, do you hear me?
Hello. Yeah.
Okay, we can hear you. Can you start sharing your screen?
Yes. Give me a second. Entire screen here. Up.
Okay, we can see everything. So let me introduce you. So our next speaker is Franco OTAOLA, University Paris Saclay. And well, he's going to talk about meshing. So it's up to you. You have 20 minutes. Go ahead.
Thank you, Joel, for the presentation. So today I'm going to present a little tool that I work for the last few months. So the idea is to present the open source tools that we have today for OpenFOAM, present Salome platform, its workflow and their limitations and the tool that I developed, and some examples and current limitations and perspectives of it. So today on OpenFOAM, we used two types of meshes, structured meshes or unstructured ones. The main idea is that the structured ones are can be aligned with the flow easily, and generally it gives a better control of the quality of the mesh and better quality of the results of the simulation. So I interested myself in this type of meshing. So the different applications that we have today in the open source world for this type of meshing are three: block mesh with OpenFOAM and several Python wrappers; Gmesh that has an interface, so it makes it a little bit easier to make the meshes instead of block mesh where you need to describe everything by text, and 3D geometries by describing by text, it's quite complicated. And Salome that has different packages such as CAD tools, and I interested myself in this software. This software it's a pre and post processing software developed by CAA, ADF, and OpenCascade, and it has several different modules with different functions. Mainly for us, there are four that interested us. Geom, that it's going to use to clean geometries. Shaper, that it's a CAD parametric modeler, such as common modelers that we use today, such as OnShape, Fusion 360, and things like that. Smesh, to mesh the geometries. And Yax, that it helps us to automate different processes. And there's more than 12 other modules. So how we compose a geometry in Salome? We create the vertices, then we create the edges connecting these vertices, and the face and the volume that it's inside of it. From the meshing part, how we construct a mesh. First, we are going to discretize the edges. Then we are going to discretize the surface, either by structured or unstructured mesh. And then from this 2D mesh, we are going to create the 3D mesh, structured or unstructured. Obviously, for structured meshes, as is the case for block mesh and other meshes, it's only going to depend the 3D mesh in the first discretization, the 1D discretization. So Salome allows us, as in block mesh, to differentiate the different directions. So we can give different refinements in each direction. And also we can tell in which direction we want the expansion ratios. For example, so we can make a geometry in different anisotropic, sorry. So the current limitation of Salome for this type of meshing, it's that the propagation groups are only going to be limited for each block separately and not for the geometry. So if we have several blocks, they are not going to communicate with each other. So yeah, and we are not going to be able to have the correct direction for every edge inside the block necessarily. So this is a lot of manual work from the user, and quite sometimes I found myself that I forgot to do something in the geometry, so I needed to go back. So the idea is that as Salome is completely scriptable in Python, was to add some smart features, if you want, to automatize everything. So the first thing that I implemented, it was the automatic propagation of the propagation groups. So this was quite easy in principle. If two blocks share one edge, they are going, the propagation groups of each block, it's going to be combined. This is going to be repeated until there's no more combinations, and we can obtain a conformal mesh of several blocks. Secondly, to ensure that all the edges are in the same direction inside of a group, I created an algorithm to classify them and create two subgroups, one in the main direction and one in the secondary directions, so the user can choose either to use the main direction or the secondary direction for the expansion ratio, for example. So the other thing I added is to use Salome to create conformal hybrid meshes. We can classify the different types of blocks in three types: quadrilateral or bigs, polyhedral prism, and polyhedrons. So the idea is that bricks are going to mesh it with a structured mesh. Prisms are going to be meshed with triangular prism, and polyhedron with tetrahedral meshes. So we can achieve a more complex geometry with most dominated by structured mesh, but also have other type of elements in the parts that are too complicated to mesh with a structured mesh. So I also added what I call parenting-child relationships, where one discretization is going to depend in other elements. So we can get a conformal meshing even if we are not having a conformal blocking of the geometry. And this obviously works for more complex geometries. So I developed also an interface tool for this script that it's going to show different information from the groups for each propagation group of the complete system, with a color interface to show each group in the geometry, the minimum and maximum length of the edges inside that group, the algorithm that the user wants to use for that group, the direction one, so we can choose the main direction or the secondary one. For the visualization, when it becomes a little bit more complex, the geometry, it's quite difficult to see it. So we can hide and show the different groups. Use a global minimum size of inside the geometry. This is going to give us a more cubish-like, more homogeneous cells inside all the mesh. Load the patch files from step files. So we are going to have one step file for the inlet, one for the outlet, and this it's going to detect it automatically. And a smart dump file. I'm going to talk about this in the next slide. So Salome has a dump tool where it's going to create a Python script of what you have done before in the interface. So the idea is that you can recover that and construct over it, or you can use it as a simple script, but it creates several geometries and subgeometries that are not going to be used in the final one. So my idea was to create a smart dump where it uses only, it has a predefined template and it saves only what we need to save. So for example, for a geometry, we go back from 21,000 lines to 8,000 lines, to 800 lines only. And it also allows us to have different capabilities, such as, for example, giving different flags inside the script. So we are going to be able to change the size of a group or the direction, that type of things. So it's going to be easier to integrate to OpenFOAM workflows. It's going to save also the geometry inside the script in a step file format. So it's going to be way smaller than saving the complete geometry. So this is going to be enabled to save space and be able to port everything and share the project. And there's not going to be any calculation in the second run of the script, as the calculation were done first time when running the script. So when we create the smart dump, it's going to get only the necessary information. And we can, before saving the smart dump, we are going to be able to change any error during the automatic detection of everything. For the moment, I hadn't had need to do this, but it is possible. So some examples, a rectangle with a demisphere, a curved plate with an obstacle, a sloshing tank, 10-tube intersection. This, I know that the blocking is not great. It was only to test the different capabilities of my code. You can see in the right of the table the time it's going to take to run the geometry. So the first time it's going to take some seconds, and when rerun it, the dump script, it's going to take way less. And creating or blocking in a CAD software, it's going to allow us to create more complex geometries. For example, a static mixer, another type of static mixer, a cyclone, or even a 3-part wing. For example, another thing that of the smart dump feature, it's that, for example, in the first static mixer, as there are some geometrical operations during the first run, it's going to take a lot of time, 2,000 seconds. But when we use the dump feature and we rerun the dump feature, we are going to get exactly the same result in 5 seconds only. Another example, it's the pump that was the challenge of this workshop. And here, for example, you can see that we are able to combine the unstructured meshing for the most complex part of the pump. And for example, for the impeller, I got 100% hexahedral meshing, and for the other part, it has tetrahedral meshing in the most complex part. So some current limitations. Salome has an automatic layer addition, but when it needs to move vertices that are in an edge of a block, it's going to fail to do that. So I'm waiting to this issue to be solved. So we are going to have a really automatic boundary layer and with a great control over it. Also, Salome has some problems over hemispheric surfaces. And this can be partially solved with 2D smoothing that it is implemented already in Salome. And even if it's really fast, it's still in serial. And obviously, the most bottleneck, it's the manual cutting of the geometry. Some perspectives, this is being implemented right now in Salome to do the 1D and 2D meshing in serial and parallel meshing of the 3D elements. This is going to highly increase the velocity of the code. Implementing quasi-structured 2D meshing of Gmesh. This is going to enable to mesh even the prism elements with quadrangular elements, even if they are unstructured ones. And the dualization of the tetrahedral meshing to have polyhedral mesh cells inside the polyhedral blocks. And obviously try to apply automatic block cutting. From the literature, I have seen several different algorithms. They are not work for every geometry, but it could be interesting to apply them each one at the time to see if one of them gets a complete block geometry. From the conclusion, I increased the capabilities of creating blocking geometries in structured meshes in open source tools, even with no conformal blockings. This it's going to help to apply them to OpenFOAM workflows, especially without the change of classic workflows where we use only text-based files. And we need to develop new tools for the block cutting geometries of the CAD. Thank you. I finish it.
Okay, thank you very much.
Any questions?
Okay, are there any questions on the floor? I do have many, but I can contact in directly. Okay, I think there are no questions on the floor, but let me ask you a couple of questions. First, you have in your title the word automatic, quite dangerous. So I wonder how automatic is this approach, because there is always some manual work to do. So how automatic it is?
My script takes a pre-cutted geometry in CAD. From there, I don't do anything. Like everything is done automatically.
Yeah, I will challenge you. Let's see. Okay, I need to test it. It is available. It is open source because I don't see
it's open source. The idea is I'm going to make a publication in the OpenFOAM journal, so I need to write it because I had my time developing the code, but I work it already with different pre-cutted geometries that people gave me without any issues. And the only problem I have seen so far it's with seam edges from cylinders and spheric surfaces. But outside of that I was working just yesterday, it's really automatic. Like I didn't have any issues in any type of geometry I tried. I tried even more complex ones. I cannot show them because it was a colleague that it was an industrial geometry to test only, but I didn't have any issues.
Okay. Final.
You are more than welcome to send me one.
Okay, no, we'll send you a couple. Final question on my side. The FDI geometry, the block con, can you share that geometry just to test it, or did you run the actual simulation using that mesh?
No, for the moment, no, because I developed it during my holidays, actually, and I didn't have a computer to test it with. But I already ran the check mesh of the geometries, and they are really good meshes in terms of quality. Obviously, they don't have boundary layers. As for the moment, you need to do an extra blocking for the block boundary layers that can be complex. But this is feasible, or if not, if it's completely structured mesh, you could use it also for as a background for SnappyX mesh and simply adding the layers after.
Okay, I think that was my last question because there is nothing on the floor here. Lex, thanks again, the speaker.
Thank you, everybody.
Thank you. And let's move to our next speaker. He's also online. Let me see here. Rajdeep, do you hear me?
Yeah, hi, I hear
Okay.
you. Are you able to?
Yes, we can hear you. Can you share your screen?
Yeah, sure.
Okay, we can see your presentation. So let me introduce you. So our next and final speaker is Rajdeep Adak from India, and he's going to talk about a GUI for OpenFOAM implemented in this Blender. So the floor is yours. Go ahead.
Okay. Thank you, Joel. Thank you for introducing me. So our objective here is to build a graphical user interface for OpenFOAM, and we hope to utilize this interface to generate cases with OpenFOAM more conveniently than it already is. So what we are going to start with is a little bit about our educational institute here. FOSSI itself is a free open source software for education, and it's a project that aims to reduce the dependency upon proprietary software and promotes the use of FOSS tools. The cool thing is we also develop FOSS tools, and at CFD FOSSI, we promote the use of OpenFOAM in academia, science, research, and engineering. And a lot of people here at the Indian Institute of Technology, Bombay, utilize OpenFOAM for their research. So we thought, why not make it a little bit more convenient, have a graphical user interface, why utilize text when you can do a lot of stuff graphically and not have some mundane task lower your productivity. So we looked into the tech stack that we could utilize, and we came up with a tech stack which is not too dependent upon various different kinds of technologies. So we initially started with Blender, and you could see that the origins are kind of a previous work that was done here at IIT only. And that was also upon Blender. But however, the older versions of Blender have deprecated now. So we wanted to update this for the newer version of Blender and make more features available. So what does our GUI do? So firstly, our GUI is named Venturial. It's available on GitHub. And it allows you to have an OpenFOAM-like workflow within Blender. Second thing is it is a homogeneous UI, especially when it comes to CFD. There are a number of steps involved, starting from meshing, solution modeling, and execution of your solver, and running the solver. So all of these things, we kind of wanted to bring them under a single hood. And the problem that a lot of people faced is they are utilizing one software for meshing. They start with, let us say, a CAD geometry that they have a software for, and then they utilize OpenFOAM to describe it in text. And again, they have to work with the command line interface to be able to run the software. So naturally, it would be better to have all of them under the same hood. But we also realize there are a number of people with different levels of skill set. So naturally, you would need multiple entry points and a more reliable data structure, which will replicate what OpenFOAM Dictionary normally does. So some general features over the top are for meshing, solution modeling, and execution running, as we have tools available for both block mesh and snappy hex mesh. We allow CAD-like geometry editing presently, but we want to make it a little bit more convenient for OpenFOAM users as well. And the good thing about such meshing is it's reversible and it's agile. So you make a mistake, you can go back and forth, and you essentially try to do stuff much more faster. Then we have solution modeling. Now, when you model your solutions, you're mainly working with scripts, but it is actually possible to do that with Python as well. So a lot of automation is possible over here. And lastly, we have some features which enable OpenFOAM commands to be run within the UI. And we also handle some errors preemptively because we kind of have an envelope of OpenFOAM. So some of the best practices could definitely be implemented. So let us look into the GUI's interface. The GUI at an interface kind of looks like this. So it's essentially the start page. It's divided into three parts. So you have your Explorer section where you can just essentially manage your mesh files and all the other kinds of solver-related files. Then you also have a recent section which keeps track of the work that you have done. So in case you do end up losing your work, it will keep an eye upon what you have done so far. So it will journal it. And later on, when you reopen it, it will bring it back for you so that you don't lose the progress. Then we also have a tiny tutorial system which allows the user to understand the interface of Blender, because naturally when you introduce another software on top of OpenFOAM, we'd want that software not to be an impediment to learning. So it would be best to have like a small tutorial system which enables the user to understand how to work with Blender. And then we have a progress navigation menu over here on the left side that essentially shows you all the options that are available for navigating through the different features that you have. So next we've gone a little bit deeper into what are the meshing related features. So we started off with block mesh, and we understood that it would be better if we were to do the composition of hexahedral primitives graphically. So all the mesh that you see over here is essentially different hexahedral primitives, and they are very easily composed and decomposed. So that again makes your workflow reusable as well as reversible. Naturally, you also need a way to distribute large blocks. So we have a very neat way in which you kind of lay it out on the floor like Lego blocks, and then you move around them very easily. Next, we also have quick data query and annotations. So a large part of the geometry is something that you need to calculate. Normally, people would use 3D geometry just to get the information of all the vertices and the rules of OpenFOAM as to how the vertices have to be aligned. And those rules and those best practices, we kind of automate here. So the user doesn't really have to go through with those processes, and can just do single clicks on these blue colored buttons that you see, and that will get you the information that you need. Next we have is annotations. So sometimes you would want to manipulate the geometry directly by interacting with it. So Blender allows you to do that. However, it's not very convenient to visualize the coordinates of the geometry, especially with respect to that of OpenFOAM, because OpenFOAM also has its own indexing strategy. So you can see that we have one indices feature over here that tells you how the vertices are indexed in OpenFOAM, and it replicates exactly the same thing that you see over here into the right image. Next is assignment of patches. So you can directly select the patches from the geometry and assign different types of patches to them. What will happen is it will take this information and dump it into a memory location within the UI. And that data can later on be utilized to generate the case. So we also have some features for curved edges. So the entire idea behind having curved edges was to make interpolation of these curved edges a little bit more intuitive. So you kind of don't have to make mistakes, especially when you're working with a large number of interpolation points. So we have some example sums over here wherein we have a simple pipe geometry, wherein we utilize the arc type edge over here, and we were able to generate something similar to that over here on ParaView. Then we also have the spline panel. So the spline panel over here is essentially replicating the same thing with spline, but we kind of wanted to test this out. So because normally in the methods that we were utilizing to replicate spline within Blender, that was not by default the same as that of OpenFOAM, because OpenFOAM very popularly utilizes the cat model splines. So we had to create our own, and that was a lot of coding work. And we eventually settled on one which kind of does the replication quite accurately, but it is not very accurate. As you can see, there are some areas where it doesn't do the exact same thing that you'd want it to. However, we are improving this, and we hope to bring something much more cooler and much more accurate than this. So next, we also have an under development snappy hex mesh dictionary generator. So normally, you can import a mesh normal STL file into Blender. But the thing that we are implementing here is we really want to separate out patches directly by looking into the geometry. So this is a feature that we're trying to implement, but it is not yet fully complete. So as you can see, there are some, some areas where the geometry is kind of composed and it's smooth, but there are other areas where it's very much divided. And because of those subdivisions, we are still facing errors. So we hope to kind of mitigate this in the future. But this is something that I wanted to mention because we wanted to bring block mesh and snappy hex mesh related tools under the same hood. So next comes as our solution modeling, because all of this is fine because we have the UI part done, but what happens underneath the UI? How is it that we are generating these dictionaries, like the OpenFOAM dictionaries? So we kind of looked into the OpenFOAM dictionary, and we figured that, so there's this thing that OpenFOAM has a single keyword that can be associated with multiple data entry values. Now, this is something that is not possible with a Python dictionary because you only have association of one key with a single value. The value could be something iterable, but that iterable would make things a little bit more difficult because you'll always have to work with that iterables methods. So we wanted to figure out something else that would do the job a little bit more fashionably, and that kind of follows the concept of object-oriented modeling. So we came up with a tree data structure wherein you can very easily declare a dictionary, and that dictionary can have two kinds of data types. One is another dictionary, or a primitive data type, which is a keyword, and that keyword is paired with multiple values that it could have associations with. Graphically, we can look on towards the right side, wherein we just represent this in terms of the nodes. Essentially, this is how normally we perceive trees as. So this is actually an n-ary tree, or like a binary tree will essentially have no more than a single node associated to a parent node. But in this case, there are multiple nodes. So this kind of theology is something that we wanted to implement here because keywords are associated with multiple data entry types. So, but to this is a data structure. Obviously, we would need ways to handle the data structure. So naturally, we had to come up with a Python API. This Python API also has a lot of purposes because we are bringing OpenFOAM's ordinary dictionaries to Python trees. We would need custom methods to work with these Python trees. Python trees will also have some keys and values, so you would need methods to edit them. So we wanted to figure out how we could do that, and naturally we ended up creating a library, like an API in itself. The good thing about this API is everything is object-oriented, and it doesn't really require a person to create those objects manually. The objects are generated automatically when you read a normal FE solution file or any kind of OpenFOAM file. It just reads the file, it identifies the kind of data that is there in the file, and it matches it with the custom classes that we have defined within our API. Once it matches them, it produces the tree exactly how it is nested within the OpenFOAM dictionary. And when we present that, we also need to understand one thing, that the tree itself is a data container, and that serves as our baseline for the GUI, because the GUI represents the tree, and because the tree is modifiable, naturally the GUI is also very dynamic, and we're going to get into that part as we move on ahead. So here we have one such implementation wherein we read a FE solution file, and it gives us all the keys that are associated with the FE solution file. And because we are able to generate this in the background, we are also able to generate the Python code for this. So you can see how custom classes were automatically generated, and user doesn't really have to manually do this process. Next is the wrappers of OpenFOAM case management tools. This is something that is currently under development. We saw that these wrappers were primarily coming with an OpenFOAM installation, but we thought, what if we could utilize the same thing, and that output that we generate with these wrappers, what if we could convert them into our Python trees? So this is something that is currently under development, and we are able to utilize the foam search tool, and we are able to generate the output directly into the terminal, which is something that you would normally do by running the foam search command itself. But the good thing is this is Python wrapped, and we hope to convert the data that we have over here into something that is more conformal to our Python trees. So next we have here is our node editor, which is the GUI part, and it shows you how we can load a custom case, and it has a single file. This is also something which is very experimental, but the good thing about this is that it's based upon a proper node editing system, which exactly replicates a Python tree. So that is what you see all over here. And we hope to make this a little bit more convenient. The UI is currently under development, and we want to bring in more features so that we can make the UI a little bit more scalable as well. Lastly, we have our run utilities, which allows time control settings for a solver. We also have ways in which we can minimize the syntax errors because the data that you're putting here is largely pre-filled. So simple mistakes in writing text is kind of avoided. We also have features wherein we can run the OpenFOAM commands from within the GUI. And lastly, because I am a developer, I couldn't help but not talk about Venturial's design. So we kept it very sweet and simple. It's object-oriented everywhere. And the good thing about object-oriented programming is it's really, really easy to code, but some people find it convoluted. And if you're amongst those people, you're really not my favorite person. But the thing is, we make efficient use of design patterns. The design pattern that we use is a model view controller, and we feel that object-oriented programming helps us. So That's basically how Venturial's design works. A little bit deeper insight tells us how multiple entry points are available. So on the view side, you have the GUI. You also have scripting capabilities with the API. And because the API works upon simple objects, it is very easily interoperable with other Python libraries as well. On an end note, I would like to mention the fact that we are not just building a GUI. We have a bigger aspiration of bringing OpenFOAM more closer to Python, because in the modern times, we see a lot of computation code is being moved to Python, and that has been a common mindshare within scientists. We also saw that while we were developing this, a lot of Python developers were interested to partake in OpenFOAM development. In fact, a lot of people in our team are computer science engineers who have no CFD background whatsoever. So because of this, we feel that Python developers also get to get some interdisciplinary knowledge, and that benefits their learning. Secondly, we also feel that a lot of students were able to learn OpenFOAM better with the GUI. And we also want to make the GUI much more feature capable and more responsible for more complex features. So what's next? We want to just give a description of what are the things that you can expect with the future development of the software. So we want to make our Snappy Hex Mesh fully featured. We also want to bring about more convenience features. We have autosave, we have auto recovery. On top of that, we also want to make our mesh controlled with parameters. We don't want direct interaction with the single interpolation points. That can kind of be utilized in various cases. Then we have a lot of focus upon the API, and we do a lot of journaling because of Python's macro system. It enables us to do a lot of journaling, and majority of the Python code that we generate is because of this journaling system. So we kind of have to develop that a little bit more to be able to consider that a full-fledged release version. And lastly, we also developed tutorials upon the GUI, so to make it much more useful. So I would like to thank the OpenFOAM Workshop, the organizers. You have been amazing, and we love the workshop so far. And the people behind Frosty team who have made all of this possible. Also, I'd like to tell you a little bit more about our team here. We also have internships, jobs, faculty partners, and workshops of our own. And if you'd like to see some of the recorded ones, you can go to the link on the right, or you can contact us to know more about us. So with that, I'd like to end my talk, and I'll be very happy to hear what you have to say. Thank you.
Thank you very much, Fred. Are there any questions on the floor? Okay, I don't see question. I have one. I have used Blender. I know it's an amazing tool, but I found it overly complicated. I hate that GUI. What do you have to say about the user-friendliness of what you are developing, user Blender? Because for me, Blender is terrible. So.
Yeah, I know. Even for me, Blender is terrible. I have used a lot of graphical user interfaces for 3D graphics and all, and Blender is not at the top of my list, and I agree with you. The thing with Blender's interface is the API for the GUI capabilities is not that developed. So that really makes it difficult. But what we did is we created an isolated OpenFOAM environment within it. That naturally means that when you're working with the geometry, you're not interfering with Blender's inherent features. So say that you have an a geometry that you have created with our add-on. Imagine by mistake you added a subdivisor into the geometry. That subdivisor is not going to work into the geometry that we have built with our add-on. And the reason behind that is how we have created an environment within it. So we really wanted to make it a little bit more OpenFOAM-like. The UI may not be really that friendly, but it is overall a little bit more understandable that, yeah, it conforms to how the general workflow of CFD is with OpenFOAM.
Okay. Is there no questions? Okay, we have one. can you?
So yeah, this is just also related to Blender, and it's not to say anything about the whole API side of this, but my experience with Blender is that there's been quite a few add-ons have been developed for OpenFOAM applications, and Blender tends to update quite a lot and break the add-ons that people have developed for it. So you end up having something which works on one version of Blender and another utility that only works on another one. So I guess the question is this going to be maintained, and is it going to be general so that it's actually user-friendly for people to install and use and not become tied to one specific version of Blender?
Great, yeah, that's a really great question. Blender has a very fast development cycle. We had this problem. We had this problem long back because, in fact, if you'd see, the origin of this work itself was on Blender 2.7, and since 2.7, there was a huge change in the interface of Blender, and because of that, we had to go through a large amount of changes ourselves. But what we did is we didn't make this GUI dependent. So you would notice that we also have a PyQt version of this tool, which is kind of available here on this slide. And this is actually built in PyQt and very well maintained by our team. Second thing is the dependency on Blender only remains in the mesh side. And we kind of wanted to reduce the dependency, because of which we created the PyVNT API. So everything revolves around the PyVNT API. And as far as Blender's API is concerned with how the interface, you would notice that all the components that we are utilizing within this interface, they are something that have remained constant all throughout the development of Blender. So we don't utilize anything outside those features. So this is essentially very proven, because whenever we install our add-on into we don't usually have problems with these features in particular as to how it looks into the appearance. What we do have is whenever we utilize a tool within Blender, which is already available. So say if I want to snap something, to snap two geometries and put them together, essentially that's how the composing feature works. That's when we kind of could have some problems, especially with those features. So we also want to minimize those, and we kind of are working upon building our own underlying tool, even though that's replication of what Blender already does. But as you said, it will reduce the dependency upon Blender's inherent features. So that's how we kind of are tackling this problem.
Okay, thank you very much for your answer. So I think we reached the end of the session. Let's thanks again the speaker for that.
Thank you.